So, what is light? If you've taken a physics class, you probably learned about wave-particle duality. Light behaves like a wave in some experiments, and like a particle in others. Experiments show both behaviors consistently. But here's what's fascinating. Modern physics has actually gone deeper than wave-particle duality. There's a more fundamental layer of reality that explains why we see these behaviors. And once you understand this layer, everything about light, about particles, about how the universe works at its deepest level, it all starts making sense. By the end of this video, you'll see reality differently. But we need to start with what scientists discovered over a century ago, and why they knew there was something deeper going on. Let's talk about what we actually observe when we study light. The famous double-slit experiment shows something remarkable. Send light through two narrow slits, and you get an interference pattern on the screen behind them. Bright and dark bands. That's classic wave behavior. Waves from each slit overlapping, reinforcing in some places, canceling in others. But here's where it gets interesting. When you detect which slit the light goes through, the interference pattern disappears. Now you get two bright bands, like you'd expect from particles going through one slit or the other. Same light. Different outcomes depending on how you measure it. Wave-particle duality became the framework for understanding this. And it works. Physicists use this concept to develop quantum mechanics, which is arguably the most successful scientific theory ever created. Every piece of technology around you, computers, smartphones, LED lights, solar panels, they all rely on quantum mechanics. So wave-particle duality is real. It accurately describes what we observe. But it doesn't explain what's fundamentally happening. It tells us how light behaves, not what light is. And that's the question that led physicists to quantum field theory. Because to understand what light really is, we need to understand something more fundamental than particles or waves. We need to understand fields. Let's use this example. There's a still pond. The water is there, everywhere across the surface. That water is a field. It exists continuously throughout that space. Now, drop a stone in. You see ripples spreading out across the surface, right? But notice, the ripples aren't separate from the water. They are the water, just temporarily disturbed. The water was always there. The stone just gave it energy, creating a pattern that moves through the field. Quantum field theory says the universe works fundamentally like this. Space isn't empty. It's filled with fields, invisible, but absolutely real. There's an electromagnetic field permeating all of space. An electron field, quark fields. Each type of particle has its own field extending everywhere. And here's the key insight. What we call particles aren't little objects floating through empty space. They're excitations, disturbances, localized ripples of energy in these quantum fields. An electron isn't a tiny ball traveling through the electron field. An electron is a concentrated disturbance in the electron field. Just like that ripple isn't separate from the water, it's a pattern in the water. This is the foundation. Fields are fundamental. Particles are what happens when those fields get excited. So when we talk about light, about photons, we're really talking about disturbances in a specific field, the electromagnetic field. Let's explore what that means. The electromagnetic field is one of the fundamental fields of nature. It's responsible for all electromagnetic phenomena, light, electricity, magnetism, all manifestations of this one underlying field. Now, fields have properties. The electromagnetic field has what physicists call potential at every point in space. Think of it as the capacity for electromagnetic interactions to occur. Most of the time, in most places, this field is in its lowest energy state, its ground state. Nothing's happening, like our still pond. But when you add energy to the electromagnetic field, maybe from an electron dropping to a lower energy level in an atom, the field gets excited. It oscillates. A ripple of energy begins propagating through the field. And that excitation, that quantized packet of electromagnetic field energy, that's what we call a photon. It's not a particle in the traditional sense. It's not a little sphere of light. It's a disturbance, a wave of energy moving through the electromagnetic field that permeates space. The photon doesn't exist separately from the field. It is the field, temporarily in an excited state. Here's what's beautiful about this. When a photon gets absorbed, say, by an atom, the energy transfers, the electromagnetic field returns to its ground state in that region, and the photon ceases to exist. Nothing was destroyed. No particle disappeared. The field just settled back down. This is what light fundamentally is. A disturbance in the electromagnetic field. A ripple carrying energy through the quantum field that fills all of space. And once you see it this way, wave-particle duality suddenly makes perfect sense. Let's go back to that double-slit experiment with our new understanding. The electromagnetic field is everywhere. When light heads toward those two slits, the field itself passes through both openings. It's not split up. The field is continuous. It's already everywhere. The field interferes with itself. Where the field oscillations from both slits align, you get reinforcement, a stronger field. Where they're out of phase, they cancel. That creates the interference pattern. That's the wave behavior. It comes from the continuous, spread-out nature of the quantum field. But when the field interacts, when it deposits energy into an atom or a detector, or your eye, it does so in discrete amounts, quanta. The electromagnetic field can only transfer energy in specific packets. You can't absorb half a photon. You get the whole quantum of energy, or nothing. That's where the particle behavior comes from. Not because there's a little ball bouncing around, but because the field exchanges energy in quantized units. Light isn't mysteriously both a wave and a particle. Light is a quantum field excitation. The field has continuous, wave-like properties, and it interacts in discrete, particle-like ways. Two characteristics of one phenomenon. Not two different things trying to be the same thing. And this framework doesn't just apply to light. Electrons? Excitations in the electron field. Quarks? Excitations in quark fields. Even the Higgs boson that you might have heard about, it's an excitation in the Higgs field. Everything we call a particle is really a quantum field doing something interesting. Fields are what's fundamental. Everything else emerges from there. So here's what we've discovered. Light is a quantized excitation of the electromagnetic field, a field that represents the potential for electromagnetic interactions throughout all of space. Particles aren't the fundamental building blocks of reality. Quantum fields are. Particles are what we observe when those fields get disturbed. And when you understand this, when you see the universe as fields and patterns and interactions rather than objects bouncing around, reality reveals itself at a deeper level. Pretty amazing, right? If something clicked that never made sense before, let me know by hitting that like button. Subscribe for more content and drop a comment telling me what you'd like to explore next. What questions do you still have? What should we dive into in the next video? Thanks for watching, and I'll see you in the next one.